Okay, it's time to do a little connection between electric fields and magnetic fields, and explain the why, I guess. If we go back and think about, remember we had a magnetic field, let's say, acting into the page, and we were going to send a charged particle in. So if I send a negatively charged particle, I wanted to make sure I had enough room in. If you remember, we learned that it's going to experience a force. Point your fingers in the direction of the magnetic field, your thumb in the direction that the charge is moving in, and the force is going to come out of the palm of your hand and act this way. So as this particle comes into the field, it's going to experience a force pushing it down. And what that force does then is it causes this particle to curve. Okay? So back when they realized all this, they thought, hey, wait a sec. We might be able to use this to figure out what the mass of an electron is. And it was actually J.J. Thomson who was the one who was the pioneer in this. Okay, Milken, a guy named Robert Milken, had figured out the charge on an electron, but they couldn't get the mass because back in the early 1900s, they didn't have any instruments that were small enough to measure that. So instead what they did was they said, you know what, if we put two plates on either side of this magnetic field and we charge them, and by charging them then we're creating an electric field between the two plates. So if I charge this plate negative, and I charge this plate up here positive, then I can play with the strength. There's going to be I just need a different color. Where's my purple when I need it? Here, purple. Found a purple marker, but I don't know where my purple pen is. Okay, so much for that. I guess we'll have to use black. The electric field's going to go this way. Well, maybe I should say the force on this electron is going to push upward. Okay, so the force from the electron is going to push upward. Because remember, we defined the direction of the electric field incorrectly because we were assuming positive charge. So the force on this electron is going to push upward from the electric field, and the force on the electron from the magnetic field is going to push downward. So this is from the magnetic field, and this is from the electric field. And if we play with the charge on the plates, we'll be able to balance the forces. And when the forces balance, then this charged particle should move straight through. Okay, so back to our electrostatic preview, we had FQ is equal to KQQ over R squared, but then we found the electric field strength, and it was equal to FQ over Q, the force on the charge divided by the charge. If we rearrange this, then we know FQ is equal to Q times the electric field. Okay, so that's an expression for the force from the electric field that's being set up by these plates. We know the magnetic force on a charged particle is QVB sine theta. So when this particle goes straight through, then these two forces must be equal to each other. Agreed? So I couldn't decide which one I want to write first. QE is equal to QVB sine theta. Look at the sine theta. It's 90, so this is 1. The Q's cancel, and it leaves us with an equation. Electric field strength is equal to the speed of the particle times the magnetic field strength. In other words, if you know how fast the particle is going, then you can figure out what size of electric field you need to balance out the magnetic field. Okay, so this equation connects the magnetic field strength and the electric field strength. Now, I'm going to be kind and say prove the units. Okay, prove that the units, and maybe let's prove them here because you know what velocity is measured in. So maybe turn off the video for a second, try the units, and then turn it back on. I'll wait for you. All right, so the units for electric field is newtons over coulombs, and the units for magnetic field is Tesla. And what's a Tesla? Well, from F equals BIL sine theta, we know B is equal to F over IL. So that means that a Tesla is equal to a Newton over an amp meter. That's really an amp. So over here, I'm trying to get meters per second. I have a Newton per coulomb on the top, and I have on the bottom a Newton over an amp meter. Now, before you sub anything else in, do a little simplification. Dividing by a fraction is the same as multiplying by the reciprocal. So a Newton over a coulomb times an amp meter over a Newton. What's going to happen to the newtons? They're going to cancel. So we will have an amp meter over a coulomb. So then you go over here and you say, oh, I is equal to Q over delta T, which means an amp is equal to a coulomb over a second. If I sub this in, or if you want, you could sub in a coulomb is equal to an amp second. That might be easier for you. Okay, so you have a meter per second is equal to an amp meter over an amp second. The amps cancel. Look at that. The units work. The equation is therefore partially validated. Partially because other things, the numbers also have to work, but at least the units work. Okay, so electric field is equal to the velocity of the charged particle times the magnetic field. And this is when there is a charged particle moving straight through the field. So what's going to happen in a question is it'll say something like, an electron is being shot through a 4 Tesla magnetic field at a rate of 4 meters per second. What must be the electric field strength to allow the charged particle to move straight through? And then part B might be, if that electric field is not there, what would be the radius of the path as a result? Because remember, when the electric field isn't there, the charge moves in a circle where the radius is equal to mv over qb. Okay, so these are connected. All right, maybe to back up just one more time, back to what J.J. Thomson did. Once he had the velocity, then he could go over here, and he knew the magnetic field strength. He could measure the radius that it would move in when he took the electric field off. He measured the velocity, so he had the ratio of the m and the q. And because Robert Milken had already found the charge on an electron, he was able to find the mass of the electron. Okay, so I'd like you to do a few questions with this equation plus a few more transformer questions today, just to make sure both transformers are cemented and this is beginning to get good. Okay.